Titrations, that's a great place to start. Yeah. Okay. Titrations. I take a look at it with that flow chart that I gave you in the syllabus on page 94. I recommend first you recognize the type of titration, then you compare the millimoles of each. And that will direct you on how to solve the problem. We can do one example of that. I think I brought one, maybe. And then the other thing that I would encourage you to stay is on page 95, sort of in the top middle. These sets of bullet points about the midpoint and the end point. So be clear on those things. Yeah, good point, Isaac. Okay, so let's see. I think I brought some titration examples. Okay, I don't think we did this one. Does this look familiar? No? Okay, I don't think we did this one, so let's try this one. This is just random point in a titration. I don't tell you where the point is. You don't know anything about this point. We're just asked to solve it. So what I would do is first determine, as I mentioned, what type of titration we're working with. We've got a weak acid and a strong base. So this would be a weak acid, strong base titration. Okay, so that's the first thing I would do. Second thing I would do is find the millimoles of each. That will tell you how to solve the problem. So for the strong base, you have 10 milliliters times 0.10 molar, and that's going to be 1 millimole. That's right, that's it. And then we've got the acetic acid, that's 50 milliliters times 0.10 molar, and that would be 5 millimoles. Okay? All right, so what is in excess? The weak acid, so we call this region the buffer region. So I'll go back to that in just a second, but you can see that the weak acid or the weak base, either, is in excess, that's a buffer region. You're going to use the Henderson-Hasselbalch to solve it. So you would approach all of these the same way, you just need to know what is in excess. Okay, so the weak acid is in excess. Let's write that out. HC2, H3O2. We're adding a base. And because the base is strong, this is going to go 100% to the right. The base will grab a proton from the weak acid, and the acid will lose a proton to the base. So get that. That makes a lot of sense, right, Isaac? Yep. Ice. Oh, you don't have to do ice, sorry. Let's just find out the amounts we have so we're all straight. You wouldn't necessarily need to write this down if you can figure this out in your head, but let me just write it out explicitly so we can see it. It started as 5, that started as 1 millimole. We're going to lose the smaller one, that's the limiting reactant, and add it to the right-hand side. That'll leave 4, 0, and 1. Well, we've just produced 1 of the conjugate base, and we have 4 millimoles of the weak acid, so we can use the Henderson-Hasselbalch. pH equals pKa plus the log of the base of the acid. The pKa you can find on the back of the test, or we would give you on the question, but this one would definitely be on the back of the test. The pKa is 4.74 plus the log of the base, this one. Just need to figure out which one's a base, which one's acid. Acid is one that has the proton. And this turns out to be 4.14. Okay? So this is in the buffer region. We'd expect in the buffer region that the pH would not vary from the pKa very much. All right, let's add a couple things to this problem that are just pretty classic in these sorts of titration problems. First of all, let's start with the easy one. So this is added, not in the problem. At the midpoint, pH equals what number? The pKa, which is 4.74 in this case. All right, let's find the volume also at the midpoint. And let's find the volume at the equivalence point. So let's find both of those. Usually it's easiest to think about the equivalence point first. Isaac, do you have a question? I'm probably going to ignore it, but you can try.
This looks like LOS.
Oh, that looks like an S. Good point. Good now? Okay, that clarified, I'm sure, for a lot of people. At the equivalence point, what two things are equal? Yeah, the amount of weak acid is equal to the amount of base that you've just added. So these two numbers would have to be equal at the equivalence point, or the amount of base would be 5 millimoles. So if the amount of base was 5 millimoles, so these two would be equal, how many milliliters of base would I have added? 50. The same as the acid in this case. So this would be 50 milliliters of the base, which is what you plot on the x-axis, or the 50 milliliters of whatever is added would have to go here. So then the volume at the midpoint would be just half of that, 25 milliliters. Okay? If you needed to find the volume of the equivalence point, not the volume, if you wanted to find the pH at the equivalence point, how would you find that? You'd have to use what method? The ice table. Yeah. If we go back to this, you know that the millimoles of acid and base will be equal. So because we have a weak acid, strong base, you'd have to use the ice table at that point. Would you expect the pH to be greater than 7, equal to 7, or below 7? Greater, because once the weak acid is gone, all that's going to be left is its conjugate weak base, so it'd be slightly above 7. Was there a question? Say your question again. What is the total volume? That's right. So the total volume at the equivalence point would be 100, because it would be 50 each, but the amount of base that you added would just be 50. And that's usually what we're asking for when we apply the volume, because usually we're starting the volume at 0. If we're starting the volume at 50 at the origin, then yes, that's what we'd be looking for. But usually it's just the amount of base, or technically the amount of titrant that was added. Any other questions on this? So between the two, you see both parts of the problem. This would be a common type of question to ask, and this would be another style asking question, asking for the volumes, the pH at the equivalence point or at the midpoint, etc. Okay, cool. Let's move on. Any other questions about titration while we're on it? Okay. Let's see, where did I put that? Yes. All right, let's do a mixed K problem, I suppose. I think I had one saved up. Let me flip over there and see. Yeah. Would you like to do a full problem on this, or just overview? Full problem? Okay. Did we do this in class? I don't think so. Okay. Yeah, I don't think we did this one. All right, we're really looking at what is part B, not part A. Part A is just in water, where in part B, it's removed, we have sodium thiosulfate, and it forms this complex right here. So we're finding the solubility of AgBr. So part A, which we're going to skip, I'll just talk about it. That's going to be AgBr just by itself. But we'll need this reaction, so I'll write it down anyways. This will be solid. These two are aqueous. So in part A, if it's just in water, how would you solve this problem? What method would you need to use? I want the solubility in part A water formula. You're going to use the ice table. So you fill out an ice table, it's already in water, that's what AQ means. Fill out the ice table 0, 0, plus x, etc. The KSP is given right here. You're going to end up taking the square root of it. That one, if you want to try, I got 7.1 times 10 to the minus, not sure what this number is, but I think it's 7 molar. Yeah, that looks about right. Okay, so that should be the answer for part A. B, this is the one that is really the mixed K problem. We're adding a second reaction. Let me write that in a different color. We're adding, we're adding S2O3 to minus. This is called hypo in the development of the film. I'm ignoring the sodium because it's a spectator ion. This entity would more likely react, what do you think, with the cation or the anion? The cation. There's two ways you could have known that. First, this is basic, so it would react with the thing that's the acid, which would be the transition metal. The other way you can think about it, that's a negative charge, it would go for the positive charge. Okay, so either way, Ag plus that. Another way you could have known that, see what I underlined here, it gives you the product, so you kind of know what reacts with what. So this would go Ag S2O3 2, 3 minus. So I actually need 2 of these to balance this out. Okay, what you're going to end up doing, so the top one is a KSP, the bottom one for part B would add a KF reaction to this, and the AGs will cancel out when you add these two reactions. Something will cancel out because you have two simultaneous reactions. So then you would end up writing the full reaction, that'd be AgBr, solid, plus the 2 S2O3, 2 minus, goes to Ag S2O3, 2, 3 minus in this case, aqueous plus Br minus aqueous. So there's now my full reaction. I have a new K for this reaction. The K for this reaction, I'll just call it K total. Because I summed these two reactions up, the K is what? Multiply, add, divide, multiply. They're multiplicative. So it'd be the KF times the KSP value. That'd be the K total for this bottom one. Now, to find the molar solubility of this new reaction, what method would I use? This also is the ice table. You're finding the equilibrium concentration, or what we call the molar solubility. So that has to come through the ice table. So you would go I, C, E. You're going to ignore the solid. It's 1 molar of the hypo, so that goes 1 there. And this would be 0 and 0. It would be minus, what I write here? 2x, because of that 2 right there. And then I would plus x on the other side. So this would be 1 minus 2x, x, and x. So K total, which we know is KSP times KF, is going to equal x squared over 1 minus 2x squared. What would be your method of solving here? Yeah, instead of using the quadratic formula, I would recommend taking the square root of both sides and solving for x. I think that would be the easiest to do. And because it wouldn't involve the quadratic, not even the quadratic, it'd be simpler than that. This is a question that you could solve the algebra for on the test. If you solve this, if you want to practice later, you should get X is 0.45 molar, which is the molar solubility. So when I added the hypo, did the solubility, did it become more or less soluble? Significantly more soluble. You would know that for a few reasons. One is, you can compare the two answers to part A and B. The part B answer is larger by about 10 to the 6th, so it's about 1,000,000 times larger. It's 1,000,000 times more soluble. Another way you could have known that is when you add something that reacts with the products, it's going to cause a shift to the right. So it's becoming less soluble if the first reaction is shifting to the right because the Ag plus is disappearing. Okay? All right, any questions on that one? It'd be a pretty classic KF, not KF, mixed K sort of question, which is what I was asked originally. Cross that out, put the next one. Good, okay. Then move this out of the way. Let's take a look at the common ion. Go in order here. So if everything goes smoothly, that video will be posted maybe Monday sometime. All right, let's just take a look at the reaction we were looking at a second ago. Okay, a common ion sort of problem would, at least conceptually, let's look at that first. Conceptually is we would be adding either Ag plus or more likely more Br minus. If we're adding Br minus to this solution here, it's going to cause it to shift more to the left. You'd actually start to see more precipitate or become less soluble. So adding a common ion is going to make something less soluble than it was originally. How that would change the math, with no common ion, I'll do that in black. No common ion, you would solve this like this, 0, 0. This is how you do part A of the previous problem, x, and then ASP equals x squared. Now let's do a different color, purple. If it was a common ion problem, you would have a number right here. So some number right here, which would be the molarity of the common ion that's added. So let's call that capital M. So you'd have a capital M here, or a capital M there. Oh, not here. In the E line, M plus X is M plus X. So then the new equation wouldn't be that, but it would be X times M plus X. And you'd end up dropping this X because it's not very soluble. So you would just solve for X now accordingly. So that's how the common ion would change the problem. It would get a number here that's not 0. That number, say M, will be here, and then it'll end up in your expression right there. And it'll end up dropping out because the solution won't be very soluble. Any questions or things you want to say about common ion? Okay. Next, delta S of the universe. So this is the second law. Second law says delta S of the universe equals delta S of the system plus delta S of the surroundings. And this is what would we say about this whole statement? It's always increasing or it's greater than 0. So that's the second law of thermodynamics. That's always increasing or greater than 0. Sometimes we'll ask you for delta S of the universe. How would you find that? Well, this term right there, you would get from delta H divided by T. I think there's a negative sign in there. By the way, the delta H is system or surroundings? System. System. would that be, yes or no, let's say I gave you a delta H for a reaction. Would that be the delta H you use here? Yeah, because the reaction is the system. That's what we're studying. So that you would find that, that's pretty common, like part A, find this, part B, find this. This could be found from either the molar entropies. That's where you give the tabulated values for each entity in a reaction, and you go products minus reactants. Or, I guess it could be given. That's possible. Let's see if there's anywhere else you might get it. You could get this, or maybe if you had this, for example, if you had delta G and H and you just solve for delta S, that could be another way you could get that. Anyway, so part A would commonly be find the delta S of surroundings, part B would delta S of system, and then part C, delta S of the universe, merely adding those previous parts up. You should get, what, a positive or negative number for your answer? Better be positive if the second law is true. Okay, so that'd be a pretty common question. You'll see it on some of the practice finals, or maybe my sample questions. Any questions about that? All right, we're rolling. Let's do delta G. Delta G, there's a few equations that you want to be savvy with going into the final. Delta G equals delta H minus T delta S. And you can put these subscripts 0 here. They can be there, they don't have to be there, both are true. Delta G is also equal to minus RT ln K, the equilibrium constant. So there's two formulas here. I would just use the formula for which you have the information given in the question. And then there's also this one. Delta G is delta G naught plus RT ln Q, the reaction quotient. Okay, so if you're asked about delta G with no 0 superscripted, that's the non-equilibrium case. So I'm not at equilibrium. And you would know that either it says it's not at equilibrium, or another way, they give you partial pressures in the question, or they give you concentrations in the question. In any of those cases, you're likely using this bottom formula. So how would you get this delta G? There's 3 ways. So I guess I could actually add another formula in here. You could use this formula if you have K. If you have delta H and delta S, I would use this top formula. If you have, I guess I'll write this in black just to be consistent. If you have delta G of formation values, where you go products minus reactants, these are the tabulated values, then you could use that. Go products minus reactants of the delta G of formation. So those are all ways to find delta G standard to put into this formula. The Q would be just products over reactants from the reaction itself. T is 25 Celsius if not given. Another way that this could be done using this first formula right here is we can give you the delta H of formations, where then you would find delta H standard. Then we can give you the molar entropies, so you'd find the delta S standard. And you would subtract them to find delta G standard, and then plug it into the bottom equation. If we wanted to be as long as possible. You would know it's that kind of question if under the reaction we give you a table of all the formation values and molar values. So that's how you know it's one of those. If we give you the delta G of formations, then you could just go straight to delta G standard, or again you could be given the K. So there's multiple ways that you get to that standard. Again, this is from the reaction. You'll recognize it by giving partial pressures or concentrations, and then you can find this. It's spontaneous if delta G is negative. Delta G is negative, spontaneous. Just in case you need a review of what the heck delta G is, it's the free energy, or it's the amount of energy that can be converted to work. It's useful energy. Delta S would be the useless energy, it's entropy. Okay, so that's why it's being subtracted off the delta H value. Another common problem you'll see in the multiple choice, again, look through the multiple choice so you see what the common problems are. But we would say something like, oh, delta S is negative, delta H is endothermic, is it spontaneous? You would say, is it spontaneous? Yes or no? No, no way. Because endothermic means positive or negative? Positive, so that'd be a positive right here. This is negative, and temperature is always positive, so that would make this value, the second term, a positive number. So that would mean delta G would be a positive number, and that is not spontaneous. Okay? All right. Let's see, that was delta G. Let's go, what will precipitate first? Next. Unless there's other questions about delta G. Those would be the pretty classic problems. Those problems don't vary a lot. So if you get a delta G problem, hopefully if you've studied, it's somewhat recognizable. What did I say we were going to do? Oh, precipitation. Yeah, let me see if I brought an example of this. I can't remember. I don't think I have another one besides what I did in class. So let me just use the one I did in class to kind of illustrate, to recap what this is about and make sure you got all the numbers. Let's say I had lead 2 plus and copper plus, and I want to separate these two. They're both at the moment aqueous, so I'm going to add something, in this case iodine, to cause one to precipitate and the other to not precipitate. So the iodine in this case, with the right concentration, will cause the copper to precipitate and the lead to be aqueous. Okay, so one's a solid, the other one's aqueous. You can pour one out of the other. And so I did an example, and basically what you need is you need to be given the KSPs of both of these in order to solve this. Will you need the ice table, yes or no? No, not for these kinds of problems. The reason is, this is different than a will it precipitate problem. This is more, when will it precipitate? So you're trying to find the moment where instantaneous, just right there, it starts precipitating. In that case, that's at equilibrium where that happens. So you can just use K, because you're trying to find out when does it start. So that's more of a when question. If you want to find out will it precipitate, then you need to calculate Q and go through there. And in that case, certain follow-up questions could involve the ice table, but at least at the first pass, usually don't. The ice table will be necessary if it says something like, will it precipitate? Then you find Q. And then the follow-up question would be, if it precipitates, what would be the molar solubility? That needs an ice table, because molar solubility can only be found that way. Does that make sense? So usually a precipitation question in and of itself is not going to involve the ice table. Unless it has a follow-up question about solubility, that's when it would need it. So all you would need to do is write the KSP for these, both of these, like this. Okay, so you write the KSP reaction. Make sure you can do that for either case. And then, let's write this. You would be given, let me put a star by what you'd be given. You'd be given this and this. Both KSPs are given. And you're usually given this and this. So those values are given. You're trying to find this. And that represents the concentration at which it will precipitate. The one that precipitates first will have the larger or smaller value of I minus. Smaller. That means you're adding less for it to precipitate. So you need to add enough iodine that is more than the smallest value to precipitate one and not the other. Okay, again, the smallest will precipitate first. Whatever has the smallest answer. So, I don't know, not all of you might have seen this question, but let me just review some of the numbers we had. When we solved this for the copper, I got 5.3 times 10 to the minus 8 molar for this one. And for the other one, so all these other numbers were given, I got 2.6 times 10 to the minus 3 molar for that. Okay, so this one precipitates first because it has the smaller number, minus 8 versus 10 to the minus 3. I need to add the amount of iodine that is between these two numbers to cause the one on the left to precipitate and this one to not. What happens if I add more than the number that is next to my pen? They will both precipitate. So if I add more than that number, they're both precipitating. If I add less than this number, what will happen? They're both aqueous. So in the middle of these two numbers is where the one on the left precipitates and the one on the right does not. That's pretty classic, which will precipitate first. Okay. Let's see what's next. Solubility, the whole chapter. Let's just take a look at the types of problems you can see. I think that would be helpful. So first of all, I'm going to flip in my reader to a couple different pages here. First, I'm flipping to get way over here. Page 111. Here's the flow chart of the whole chapter. There are KSP ice problems, which I'll mention this in a minute, and KF ice table sort of problems. Okay? So you would want to be able to find the molar solubility, which is the most common. In that could be the common ion effect. And under that can be some mixed K problems. I'll show you the list in just a second. And then there's also the precipitation sort of questions. Again, the will it precipitate will only be followed with an ice table if we're asking for the molar solubility. We may or may not ask for that, so you just need to look carefully. So now I'm going to flip. There's a little summary of types of problems from this chapter towards the end on page 120. So let me summarize all of these. Make sure you can do each of these kinds of problems. First is what I call the simple ice table. This is where you have one compound. That's it. It's aqueous. It's by itself. Usually KSP is given and you're asked for the molar solubility. Again, anytime you need molar solubility, you have to use the ice table. The second type of problem is a common ion question. It's really pretty much identical to the first type, except you're going to have a non-zero number in the ice table. Whatever the common ion is, that concentration needs to go in the I line of the ice table. So 1 and 2, however, are really similar. Okay. Next, number 3, this is the one I was talking about earlier, precipitation. You're not going to use the ice table. Just depends the type of question you're given. The will it precipitate, this is predicting the future of sorts. So you have one compound and you're going to use Q. It is not uncommon in these sorts of questions, really part A or maybe part B as well, to do a dilution problem. I mean, it's not uncommon for us to say we're mixing these two things. Here's the molarity and volume of this one. Here's the molarity and volume of this one. They're mixed. You'll need to find the new molarities in order to solve the problem. So that's not unusual. It's often a combo problem. Fractional precipitation is what we just did. This is which one will precipitate first. So you're finding at what point does this precipitate. So that's why you can just use KSP here, not Q. The fourth type, I call the simple KF problem. This is where you have one compound, but it's specifically a complex ion. You'll know it's a complex ion because you have a metal in it. Is there a question?
120.
Somebody said 120 and I believe them. Yes, I have confirmed that. 120 in the reader. If you don't have the reader, it's in the library. Okay, so There's one complex ion. You're going to use the ice table. This one also could involve M1V1 equals M2V2 if it says we're mixing two things together. Let's just do a little review of that. If I'm mixing two things at equal volume, which is our favorite way to word this problem, what will happen with the molarities? They will both go in half if you're doubling the volume, or it says we're mixing at equal volume. That's a fun way for us to word it. Okay, you're going to use the ice table to solve this. It could involve stoichiometry, so just be aware. The stoichiometry video that I gave as a video a couple weeks ago on campus is kind of a classic example, and we did another classic example in class as well. These especially don't really get harder or easier, they're just that. The same with 1, 2, and 4 don't really get harder or easier. I'll mention something about 3 in just a minute. 5. For most students, this is the toughest type of problem because it involves two reactions. How do you know it's this kind of question? If you have one compound in another compound that's not water. So we've got one compound in another compound that's not water, it's this for sure. Okay. So how do you solve this? You're going to have two reactions. One of those reactions will be a KSP. That's what this means here. Right where my pen is. One of the two reactions, usually the prime reaction, is going to be a KSP, something dissolving. The second reaction will either be a KF, that's what we just did with the hypo question, or it will be an acid-base. We did one of those in class. So it'll be a combo of those. You have to add the reactions, and K is get that from the two K values up here. So usually they're multiplied. And then you have to use ice. So it's ice on top of adding reactions together. So these are always done the same way. They just traditionally freak students out, even though they're always the same style of solving. Now I want to add something to number 3 right here, unless there's a question. Okay? From number 3, the next page, 121, of the reader, occasionally, so there's a couple notes. One is, we can often use the dilution formula on number 3. I think I mentioned that already. Occasionally we'll always ask, or we can ask, what is the percent unprecipitated on either type of precipitation problem. I did an example of that in class. And then, if we want to be really crazy and have a lot of fun on the final, we can combine any of the 5 types of problems together in one problem. Yeah, it's that fun. Let me show you a common way. The hypo problem was this example. Remember there was a part A that said, what's the solubility in water? That was this. So a simple ice table. And then it said, oh, but now I'm adding hypo. That made it this. So that was a 1 and a 5 together at the same time. That's the hypo one we just did. Okay, any questions? So, any questions? Also add, once you identify the type of problem, just like titration, you'll always solve them the same way. So, when you might want to use this if it's helpful when you're doing some of the practice problems on the final. Identify it and then see how it's always solved in the same sort of style. Any questions on that? Okay?